All right, so this last section of Together Problems that we're going to do is primarily going to focus on this summary chart. So make sure you've watched the video for 14.8 to 14.11. We're going to come back to this summary chart a lot. And I thought the easiest way to do this to save time for me and you was to just scan the answers in for the Together Problems, and then I can talk us through them. So the first Together Problem that we had is going to be number 99. Okay, now if you look at 99, now this isn't quite the answer yet, it's the background. But what 99 is asking you to do is it's asking you to arrange the following 0.10 molar solutions in order from most acidic to the most basic. Okay, and they're 0.1 molar. And I wanted to scan this whole thing in because I like the breakdown that it gave you in terms of some hints, and it's a good time to kind of figure out, okay, what are we talking about? Because one of the things you've heard me mention this whole idea of figuring out the species that are present. Okay, and so whether it's a strong acid, a strong base, a weak acid, or a weak base helps us figure out if it's a neutral, what the pH is of that solution. So just as a reminder, here are some things that we need to remember. Whoops, there goes, I don't necessarily want to highlight all that. But number one, we got to know the strong acids. Been throwing these at you for a long time. Hydrochloric, hydrobromic, hydriodic, nitric, perchloric, and sulfuric. And as a reminder, sulfuric is the only one that is a polyprotic acid. Okay, now the strong bases primarily are the group 1s and the group 2s. This is a more significant list. The only group 2 that's really common that's not necessarily on this list is magnesium hydroxide. But for the most part, it's why we don't see magnesium hydroxide much in acid-base chemistry. But these are your strong bases, which are group 1s and group 2s. All weak acids have a Ka value of less than 1, but greater than Kw. Okay, so it's greater than that 1.0 times 10 to the negative 14th. Some weak acids are in table 14.2. All weak bases will have a Kb value less than 1, but greater than Kw. Some weak bases are also found in table 14.3. Please don't show me that again. Conjugate bases of weak acids are weak bases. For example, I'll have a Kb value of less than 1 but greater than Kw. All right, and this is going to show you, some examples in 14.2. All the conjugate acids of weak bases are weak acids. Okay, so they have a Ka value of less than 1. The example you guys can read, but this is just kind of summarizing it. Alkali metal ions and heavier alkaline earth metals have no acidic or basic properties in water. Remember, it was just those highly charged metal ions that we saw for the transitions. And all conjugate bases of strong acids have no basic properties in water, with the exception of the hydrogen sulfate. Okay, so let's look at these ideas and try to figure out what species are present, and then try to figure out what the order is for these. So if you look at the first one, you've got potassium hydroxide. Okay, potassium hydroxide is a strong base. So if we know it's a strong base because it's group 1 hydroxide. Okay, if you look at potassium chloride, okay, potassium is neutral. Potassium and chloride both really have no significant acidic basic properties because they're so weak. They essentially don't have anything going on because potassium would come from potassium hydroxide. It's a strong base. The chloride comes from hydrochloric acid, and again, it's so strong that there's nothing there either. So they're neutral. Neither one trumps it. Okay, potassium cyanide. Okay, cyanide is a weak base. And the way to find the Kb value, okay, here's Kw and here is Ka of hydrocyanic acid. Okay, so that's where, we can actually find the Kb value for this one. Ammonium chloride. Ammonium is a weak acid. Its Ka value is 5.6 times 10 to the negative 10th. Chloride's not going to trump it. It's so weak. It's kind of just like hydrochloric is off the charts in terms of strength. The chloride ion is off the charts in terms of being a weak conjugate base. All right, and then you have hydrochloric acid, which is a strong acid. So now we've got to go back to ranking them. So hydrochloric is going to be the strongest, most acidic. Then we need to use the ammonium chloride, and then our potassium chloride, potassium cyanide, and then potassium hydroxide. And again, where the reason that potassium chloride kind of trumps in the middle here is that it's got that neutral neutral pH. So we still kind of fall in the middle of those as well. Okay? Alright, so there's the order for those, then you've got the strongest base out here. Alright, now let's go ahead and look at, and this again, the salts can be tricky. You got to spend some time kind of wrestling with it. May not be a bad idea to read the book to figure out where we get those from. Alright, the next together problem was 104. Okay, and for 104, what they were asking you to do is, let's see, calculate the concentrations of all the species present in a 0.25 molar solution of ethyl ammonium chloride. Okay, so we've got ethyl ammonium chloride, which is this formula here. Now, we still, particularly with the way that we treat the substances, okay, the chemistry that's going to take place here is that, first of all, you're going to get this split up into two ions where you're going to have ethyl ammonium and then you're going to have chloride. So that's going to first split up. And then the other thing that you need to remember is, particularly when you see that NH3 on the end, that's where the hydrogen chemistry is going to take place. So the ethyl ammonium ion is a conjugate acid of a very weak base, okay, which would be this compound right here minus the extra hydrogen ion. So it's got a Kb value. Here's the Kb value for this weak base. This would have to be given to you in a test or quiz scenario. You wouldn't, the book wants you to go look it up. But as true for all conjugate acids of weak bases, it's also a weak acid. Okay, so the chloride ion is going to have 0 basic or acidic properties, so we ignore it. So we got to solve the weak acid problem to figure out where this is going to go. Alright, so if I come down here, here is my acid base, setup. I've got my initial concentration of 0.25. What I'm looking for is the concentration of all of the ions. So I set it equal to, the other thing that happens on these is, if you remember, if you have a Kb, we have to find Ka using Kw. So they do that. Here's the Kb value. We use Kw to find the Ka value of the conjugate acid. Okay, so this is where this all of a sudden back and forth stuff is going to come into play a little bit more. But anyway, we set up the equilibrium expression. The assumptions work out for this one. So the x is going to be 2.1 times 10 to the negative 6th. It wants to know the concentrations of all of the species, so we need to be able to go backwards and kind of look at our concentrations on these. Our hydrogen ion as well as our weak acid are going to have the same concentration. We also, when we subtract the small x, it still ends up being 0.25 for the ethyl ammonium ion, and then the chloride ion wasn't touched either. And the other thing we got to remember is, since we know hydrogen ion, we now have a way to always figure out hydroxide using Kw as that intermediate, kind of going back and forth. Okay? Alright, so that is 104. Then the last one that we needed to do was 112. So if we come down, alright, what 112 is asking you to do is asking you the following solutions if they are acidic, basic, or neutral. Okay, and for those that are not neutral, we want to write a balanced equation for the reactions causing the solution to be acidic or basic, and that points you to the relevant Ka and Kb values that can be found on 14.2. Okay, so again, potassium chloride. Potassium comes from a very strong base. Chloride comes from a very strong acid. They are essentially neutral. They're so weak, they're not really going to influence pH very much. Okay. Now, if we look at letter B, okay, we have our combination here of where we're going to split off, okay, into ammonium and then the anion. And they're both weak, okay, so we're still looking at neutral. The ammonium is a weak acid, and the acetate, that's acetate, is going to be a weak base. The acetate ion is a weak base. So then what we have to do is, since the Ka for both of these is actually equal to each other, we know that the pH is truly 7. Okay, and this math down here is just justifying that, because since ammonium is the conjugate acid of ammonia, We can find Ka using Kw, and the Ka value for ammonium would be 5.6 times 10 to the negative 10th, whereas the acetate ion is the conjugate base of acetic acid, so you also could work backwards. It's just showing you that the Ka and the Kb values are equal, so it's justifying the fact that it's neutral. Okay, now for letter C, we're going to split this off into chlorine, or the chloride ion, and our organic acid as well. And the chloride is not going to have any properties because since it comes from such a strong base, or strong acid rather, it does not influence pH, but this is going to be a weak acid. Okay, so again, just as a reminder, you can, if we know it's a weak conjugate acid of this base, so we can always go backwards using Kw to always find the opposite Ka value, and that's where the 2.28 times 10 to the negative 11th, that's just the Ka value for this weak acid. Okay, now if we look at letter D, you have potassium fluoride. Again, potassium does not have an effect because it comes from such a strong base that it is a super weak acid. Fluoride is basic. It's a weak base because hydrofluoric acid is also a weak acid. So again, if here's the Ka value of hydrofluoric, you can find the Kb of the fluoride ion by using Kw. If nothing else, I'm trying to drive this point home right here, is if you know one, you can use the other using Kw. And then letter E, you have ammonium fluoride. Ammonium is a weak acid, fluoride is a weak base, so they are weak, but what we then have to do in order to get the definitive answer is compare the Ka values and the Kb values of both of those substances. Now we already found them up above here, okay? We found the ammonium Ka value right here of 5.6 times 10 to the negative 10th. The Kb value for fluoride is right here, 1.4 times 10 to the negative 11th. So since the Ka is greater than Kb, the solution is going to be acidic. Okay, so that's how we make that definitive answer. And then last but not least, you have a cyanide compound with a weak acid. Okay, and so this one's going to be basic. You have the weak acid, and cyanide is a weak base. So again, you have to go to the Ka and the Kb values to determine them. We already found the Ka value of this one up above. You can find the Kb value of cyanide by using the Ka of hydrocyanic acid, and since this one is greater, it's going to be a basic solution. Okay, it's tricky. I know it's tricky, but you know, go back to that information, go back to that chart, and hopefully we can get it worked out. Okay, hope that helps.